So it's a great pleasure to have our own L.Frolov talk to us about on the joint evolution of a scalar point charge and its field in one space dimension.
Hello, everyone. It's great to be talking here again. So today I'm going to give you a presentation which is actually very similar to a previous presentation that I gave a few months ago with Samuel Leigh. And the purpose of this talk is to make an amendment, a correction to the previous talk. And we will discuss the correction and its implication on our research. So the layout of the talk is very similar to last time. We study the physical system composed of a scalar field coupled to a point particle in one spatial dimension. And using just the assumption of local conservation of energy, we will rigorously derive the force law, which acts on our relativistic particle. Normally, in textbooks, you would find that physicists use the principle of least action, but we will show that the force law, which the principle of least action gives rise to, is not well posed, and so we will instead do this. And then once we have our dynamical equations in hand, we're going to show the well-posedness of our joint evolution by proving the existence of a unique global and-time solution to the initial value problem. And lastly, we're going to take a look at the dynamics of our system, and we will prove some asymptotic behavior for our trajectory that was not present in our last talk. In particular, we will prove that the particle will asymptotically tend towards rest due to a self-force term, which is oppositely proportional to the velocity. So wherever our particle is moving, we'll find that there is a self-force term which is actively dampening the motion of the particle. So in particular, I'd like to start by offering some motivation on why we wish to study the joint evolution of scalar particles in 1+1 dimensions. And ultimately, our goal is to just generally study the joint evolution of particles and fields, most likely in 3+1 dimensions. An example of a joint evolution of particles and fields in 3+1 dimensions is the Maxwell-Lorentz regime for electromagnetism. However, this very famously does not give rise to a well-posed joint evolution problem, because the force law, the force which acts on a charge, relies on the evaluation of the electromagnetic field along the trajectory of the particle, and yet precisely the location where this electromagnetic field is undefined is along this trajectory. And so we find that Maxwell-Lorentz does not give rise to well-posed joint evolution problems using this force law. And in a very recent novel paper by our own Michael Kiessling, he proposed a new force law, which instead of being based on the principle of least action, was instead based on the weaker assumption of the principle of energy, local energy conservation. And then also in the audience, Vu and Maria used this Kiessling force in order to prove the well-posedness of the joint evolution problem for electromagnetism in 3+1 dimensions, but in the BLTP, Bopland-Thomas Podolsky regime, which was very exciting. However, the self-force which is found in that paper is quite complicated and quite difficult to really understand. And so ultimately, the goal of studying scalar particles in 1+1 dimensions is to act as a toy model for us to play around with and to better understand the self-force that charged particles exert on themselves. In our last talk, we discussed the connections of scalar particles to gravity, and we ultimately concluded that we were not sure what kind of force of nature scalar particles are most likely associated with. And since then, we have updated this. So the study of scalar particles, we now know, can be motivated by its connection to the residual strong force. And this is based on Yukawa's work back in the mid-early 1900s. Yukawa considered a potential for a stationary scalar particle, and this was given by the following equation. And when you solve for this in n dimensions, we find that in n equals 3, you end up with something very similar to the Coulomb potential, except in the case that your field is massive, in the case that you have some alpha, it is actually going to exponentially decay. And this is precisely what gives rise to the short-term interactions which are found in what's called the residual strong force. Something I'll note is that the residual strong force and strong forces in general really should be examined via quantum phenomena, as a quantum phenomena, not as a classical phenomena as we're doing here. But this is just the motivation of classical scalar fields. So in n equals 1 dimension, which is what we're studying, in the case that alpha is greater than 0, we also have an exponential decay. We also have short-term interaction. But in the case that alpha is equal to 0, we do not. And in fact, our interaction is not short-term. If you take the derivative of this scalar potential, you'll find it is constant essentially everywhere. And in this talk, we will study this last case, n equals 1, alpha equals 0, because it is much simpler to study. In the case that you have alpha greater than 0, you have Bessel functions, and it is very complicated. Since we just want to work with this toy model for now, we will consider this much simpler case. So our setup, right, we should consider setting up our joint evolution problem. We consider relativistic flat space-time, R11, with the following signature for our metric. And our action is given by the following Lagrangian density, where there are two types of term in the Lagrangian density. The first one is the scalar field, the massless scalar field. And the second term is the action given by our particle. And in particular, you'll notice that normally this Lagrangian density would be simply m, but instead we have here m minus au in order to ensure that the particle is coupled to the scalar field. And here, m is the bare mass, a is the charge, and z mu is the space-time position of our particle. It only has two components, z0 and z1. Notice I'm calling this m the bare mass. Sometimes the literature refers to m minus au of z as the bare mass, but in this talk we're going to call this the bare mass. And also delta squared is the 1 plus 1 dimensional delta function on space-time. Okay, so after we take formal variations of our action, if we take the principle of least action, then we are given the following equations of motion. If we vary with respect to u, then we get the field equation. And we see here that our particle is acting as a singularity in the derivatives for our scalar field, similarly to electrodynamics. And then we also have the force law, which is given by varying with respect to z. And we find that the force law is given by this following equation. Notice that the left-hand side is expressing the rate of change of this p star term, which is m minus the charge multiplied by the field evaluated along the trajectory of the particle. And one thing that we will see throughout pretty much all of our calculations is wherever you would find mass, you will find that it will instead be replaced with this m minus a times the field evaluate the location of the particle. And so we go on to call this term, which we call p star, to be called the dynamical momentum of our particle. And also the this m star we define here to just be what some people would call the bare mass, we call the dynamical mass. Wherever you would expect momentum and mass to show up, instead this dynamical mass and this dynamical momentum will appear instead.
Maybe you want to say that the little u is the unit tangent.
Yes. This refers to the proper velocity, which has two components, u0 and u1. Thank you, Shadi. So now that we have, if we take the principle of least action, we have our evolution equations. And so given an arbitrary world line, we can solve for the field. And the way that we do this is we use linearity to split up our field into two different parts. The freely evolving initial data. And here the initial data that we are considering is the potential which is generated by a stationary particle and perhaps some incoming external radiation. And also, we refer to the terms of this freely evolving initial data, which only depend on the external radiation as the external radiation field. So V satisfies the wave equation, but with V1 and V0 as the initial data. And given an arbitrary world line, U source is given by Duhamel's principle. And in other words, what this integral equation is telling us is that the longer our charge stays in a single place, the more this U source is going to grow. In other words, the charge is acting as a source for the field. Okay. However, an issue that we run into is that for any arbitrary world line, we find that the derivatives of our field are undefined along the trajectory of our particle, which is precisely the same problem that we ran into in Maxwell's electromagnetism in 3+1 dimensions. And this is an issue because our force law relies on the derivatives of the field along the trajectory of the particle. And so we find that the force law, rather the joint evolution problem, is not well posed. The force law is non-admissible. My favorite way of saying this is that there are no joint evolutions where our action is minimized. And so at this point, we are at a loss. We are not sure what to do, unless we recall that typically the principle of least action would imply the total conservation of energy. And so perhaps if we want to come up with a force law which replaces the undefined terms in this equation 10 with perhaps other terms which are well defined, then perhaps instead of taking the principle of least action, we should take this weaker assumption of conservation of energy. And that is precisely what we do. Once we take our assumption to be given by this, where T mu nu is T mu nu p is the stress energy of a particle, and T mu nu s is the stress energy of the scalar field, then we can derive our new force law. So this brings us to the first theorem of our paper, which is if you suppose that the stress energy tensor of your scalar field is locally integrable around Z1. Notice that this assumption is not always adhered to by all field particle systems. For instance, Maxwell-Lorentz in 3+1 dimensions does not have this property that the scalar field, the stress energy of the scalar field is locally integrable around the path of the point charge. So if this assumption holds, which it does hold in scalar fields for 1+1 dimensions, if we assume conservation of energy in this following weak sense for all tubular regions around the particle's world line, then this will return the force law. This will return the following force law. I will note that conservation of energy really only makes sense in the weak sense because our stress energy tensor T is going to be very singular along the trajectory of the particle. And so it does not quite make sense to talk about derivatives of the stress energy. But if we talk about it in the weak sense, then it does make sense. And we find that it gives rise to a unique force law, which is given by equation 15. Here, this bracket x1 equals z1 denotes the jump. So the stress energy tensor of our scalar field, which is over here, is a function of space and time. However, at the location of the particle, it jumps, similarly to how a Heaviside step function jumps at 0. And so what we are doing here is evaluating this jump. And using our field equations, we may explicitly calculate this force. And we find that it is given by equation 16. I'd like to backpedal a second because some of you will notice I have an exclamation point here. And this exclamation point is supposed to signify importance. This is an important equation because this is precisely the place where we made our mistake in our last presentation, a mistake that was very graciously pointed out by Vu and Maria, who I believe are in the audience right now. We would like to thank you very much for pointing out this mistake. In our last presentation, this equation had an extra minus sign here. And in particular, the place where this extra minus sign, where this mistake was coming from, was from a misunderstanding of this Stokes' theorem that we have in equation 14. And essentially, it was an error regarding the calculation of this normal vector here, where this is normal to the surface of the tubular region. It was an issue with vector versus covector. Ultimately, we ended up with an extra minus sign in a place where we weren't supposed to, and this led to an extra minus sign in our force law. And this extra minus sign actually does have a very large effect on our dynamics. So in particular, what we found is that once this is fully corrected, the force which acts on our particle is given by this equation 16. And you'll notice that there are two types of terms. This term over here depends on the external radiation. And this is the term that perfectly matches up with what the principle of least action would predict, right? This is the exact same force law from the external radiation as in the principle of least action. But that term, which depended on the derivative of U source evaluated at the location of the particle, has now been replaced with a new term. And this new term depends solely on the velocity of the particle, not on any sort of external radiation, and should really be best described as the self-force that a particle exerts on itself. Notice that it points oppositely the direction of the proper velocity, meaning that it is a restoring or a dampening force. So you'd expect that as the particle moves in one direction, what this self-force seeks to do is push it back towards rest. Right. So conservation.
I have a question. Can you go
Absolutely.
back to the minus a squared over 2 u1? That's the restoring force you said, or the self force which acts as the restoring force, right? Mm-hmm. Okay. And then my question is this true in higher dimensions? This T mu nu being locally integrable, implying force law such as 15.
Yes. So if T mu nu is locally integrable, then the people that you should be asking are in the audience right now. Vu and Maria prove that in the case of in the BLTP regime, you get a force law which I wouldn't quite say is it doesn't have this exact same form because what we're doing here. One way of thinking about this is
because jump doesn't make sense in 3 dimensions.
What do
you mean by jump?
This is codimension of the singularity is 1 here. So it makes sense to talk about the jump across the singularity, right? So the trajectory is a 1-dimensional curve in a 1 + 1 dimensional space-time.
Okay.
Right. But in 3 + 1 dimensions, the trajectory is still a 1-dimensional curve, but now in a 3 + 1 dimensional space-time.
Yeah.
So even though the force law that Michael has is still well defined for something like BLTP, it wouldn't be expressible in terms of a jump because the jump doesn't make sense.
I think the jump is replaced by some kind of averaging procedure.
Some kind of, yeah. It's like a non-local term, right?
I see. Okay.
There's also like a surface integral interpretation, right? Where you take the surface integral over. So like this would be taking the surface integral over a ball that's shrinking.
Yes, I think so. Yeah, I think that's what replaces the jump. Yeah.
Yeah. So Eric, if you consider when we say jump is consider a function which jumps at a point. What I mean is taking the limit from one direction and subtracting the limit from the other.
Okay. And the limits aren't equal.
Yeah, and the limits aren't equal. When we are in higher dimensions. So another way of interpreting this is as a surface integral in one dimension. A surface integral in one dimension literally just means taking the evaluation at one point, subtracting by the evaluation at another. In higher dimensions, it
would be a
generalizes.
I see.
Yeah. But I think that's a great question, and the study of these types of systems in higher dimensions is currently being done. I know, I believe Vu is also studying the case of, well, I believe that there are many people working on generalizing these kinds of results to 3+1 dimensions for different types of particle field systems. Okay, so, all right, so conservation of energy has provided us with a very familiar force law, but the undefined terms have now been replaced with something well-defined, the self-force terms. However, there's an argument to be made that that force term from earlier really described the rate of change of the dynamical momentum. But what we are really interested in is understanding the long-term behavior of our particle, and that is much better described by the rate of change of our proper velocity. So we use the chain rule, and we find an explicit form for the rate of change of our proper velocity. And in particular, you'll find that these two terms on the right are given by the external radiation. As I said before, they are the same terms that you would normally find if you take principle of least action. And now the undefined terms are now replaced with this term instead, this minus a squared over 2 u1. And so kind of what you expect is that this proper velocity of our particle will decay once all of the radiation has passed and these force terms vanish.
So just one more question. Back when you had the minus sign mistake, you would have a minus or a positive a squared over 2 u1, right? So then this is why it wouldn't have been a restoring force. Then it would have gone off to infinity.
Yes, although it wasn't quite. So the mistake was right here. It was in this. This would have been a plus a squared over 2 u1. And this wouldn't quite be plus here because remember we used the chain rule, and that chain rule calculation was correct. So what we had here was a term that was quite complicated, and it looked very unnatural. And intuitively, the three of us, me, Shadi, and Sam, had some issues with it, trying to understand it. Instead, what it caused was the particle to asymptotically tend towards a very specific velocity, which was given by the square root of 3 over 2. It seemed Lorentz non-covariant. All of these issues have been thanked very much thanks to the help of Vu and Maria. We are very grateful for this. But we now find that, yeah, we have this self-force term instead. So,
anyway,
however,
let me also chip in, Larry. It's still a very puzzling self-force. Because say if you don't have any applied fields, that means the capital V are gone, right? So then for some mysterious reason, so the particle should come to rest. Now, why would it do that? Why? So this is Lorentz covariance would say that if I go into a moving system, right, then the particle will, if it was at rest in its own rest frame initially, then it will now move with a constant velocity. But according to your equation, it should again come to rest again. So this looks a little strange to me.
It does look strange. And I have an answer to your question about why this is happening, even in the case of after the, after.
So wait, I just so that I understand Michael correctly, like if there was no V or anything and the particle had a certain velocity, I mean, I know this is weird, but just suppose that you're in one frame and then the particle in that frame had a certain velocity. Would this imply that after a while this particle is going to decay to zero in the original frame you started with?
That's what it seems to say, man. That is very weird.
I see. So then that's why the Lorentz covariance is.
It's not a Lorentz covariance.
It's kind of wacky.
This is great because I actually, I've been preparing for this question because I've been thinking about it a lot. And the answer is, it is important to note that these formulas, this formula right here, was evaluated in a frame of reference. if it was evaluated in the frame of reference that our particle was initially at rest. So if we were to move into another frame of reference, then what would happen is the particle would be perturbed by some radiation, and then whatever velocity it started out with before the radiation came in and perturbed it, it will asymptote towards that velocity. So it is Lorentz covariant, and this is something that I've checked, although it's not included in the paper because, like I said, all of our equations here are Lorentz covariant, and so I didn't feel a need to complicate all of my equations by introducing an arbitrary rest frame. So we moved into the rest by moving into an arbitrary frame.
So is the assumption on that V that it is some kind of a pulse that is very localized and moves over the particle? And so basically there's only a finite interval, time interval where there is an interaction?
Yes.
Okay.
So we take the radiation to be initially compactly supported.
Oh, okay. Okay,
Yeah.
so yeah, then it starts making more sense, even though it's still interesting to see that apparently, well, at least in this setup, it seems that the V field, the radiation field, cannot impart a certain momentum onto the particle at the expense of losing some of its own, like in a scattering scenario. So let's think of two billiard balls for simplicity. One is at rest in its frame, and there's another billiard ball coming. If they are of the same mass and they hit fully, then one gets kicked and starts moving, the other one stops. And so here, one billiard ball could be the V and the particle is the other billiard ball, but that kind of scenario doesn't seem to happen. It's always coming back to rest. So that's a little bit.
Yes, but actually, no, that's a perfect example. I love this. Okay, this is great. So the reason why that's happening is because once the particle starts to move, the field that it's sourcing starts to change.
Sure.
So, and this is my next part. So once your particle is perturbed by some sort of external radiation, the motion of the particle is going to generate motion in the field that it sources. And originally, that motion in the field that field that it sourced had no energy whatsoever, or rather, no energy locally around the particle, is what I'm going to say. It has infinite energy around the entire system, but locally around, if you take like an arbitrarily small interval around the particle, it becomes arbitrarily small. However, once the particle starts moving, it generates this like local kinetic energy in the field that it's sourcing, and this is increasing the field's kinetic energy. And so in order to the sourced field's kinetic energy, and so in order to in order for the total energy of the system to remain the same, to be conserved, the source field's kinetic energy is sapping the particle's kinetic energy. And that's what this self force is. So I have a simulation for you that kind of expresses what I'm talking about. So suppose we start with a stationary particle, and you can see here it's being perturbed by some radiation, and it's moving. And while it's moving, these blue lines represent the field that it's sourcing, not the external radiation. You can see that it starts to wiggle around as well. And it's like sending off waves almost. And those waves have energy. So the billiard ball analogy that you're talking about is actually quite perfect, because what we find is the radiation is like one billiard ball, and then it hits the particle. But then as the particle is moving, it's sending out, there's like another billiard ball that's being sent out in the form of the field's energy. And that's coming from the particle.
Okay, and one sees also in that simulation, I don't know whether you did that deliberately or whether it's really a solution to the equations. You can answer that, of course, but while the particle does come to rest again, but it doesn't come to rest at the original location. So that means in this sense, there is a type of effect of the field that is a kind of a memory, so that it remembers that there was something. So when you look at where the particle is, after a while, then it's no longer at its original position. So that means something must have happened, even though it is at rest. Yes.
I mean, it was originally at rest, and then it moves, and then it asymptotically tends towards rest at a single point. But that point, like you said, is very much not where it originally was. Mm-hmm. Yeah.
Right. So in this sense, one sees that there is an effect. It's not that after the wave passes through that everything looks like before. It does not. So it's.
Yeah.
Okay, very good.
Okay, so I hope that this gives you all a nice intuition about what our self force is doing, and why we expect it to exist. So now that we have our self force and we understand it a lot more, let's try to make sure that we prove the well-posedness of this force law, namely that if I have some initial data, it will give rise to a unique global and time solution. And this joint initial value problem is really, while it is messy, it is best proven using these, using the variables, the dynamical variables being the position of the charge, the dynamical momentum, and the scalar field U. You'll see what I mean when I say it's messy. It's because when we write down the derivative of the position of our particle, it's given by this v, but v, when written in terms of the dynamical momentum and the dynamical mass, is given by the following. Without loss of generality, we take it to be at the origin. The rate of change of our dynamical momentum is given by the force law from earlier. Notice that there are some extra terms here, and that's because this is now dp star over dx0, not over d tau. And this term over here represents the self force term from earlier, just rewritten in terms of dynamical momentum and dynamical mass. And this is the external radiation term. And lastly, we have the field equation. We have the full field equation. Particle is sourcing the field, and we have our initial data. And so this leads us to another main theorem in our paper, which is that for any set of particle parameters with our bare mass greater than 0, and for any set of functions with initial data with these conditions, the joint initial value problem admits a unique global and time solution. In particular, we take partial 1v bounded in Lipschitz for all time. That's like a very standard assumption to take when trying to prove well-posedness of particle trajectories. This additional assumption that AV is less than 0 everywhere, this just has to do with the sign of our radiation. And there are not many ways I can physically motivate that right now. In the one particle case, it is a lot easier to motivate in the n particle case.
You mean AV0?
AV's, no,
so AV.
Yeah, so V is the solution to the wave equation where the initial data is given by V0 and V1. So I'm saying that V0 and V1 give rise to a V with these properties. So yeah, here we're taking this assumption. One way to think of it is that we want to ensure that our dynamical mass, which was given by m minus AU, that this only increases once our radiation perturbs our particle. If it decreases, then we might run into a situation where it decreases it too much and the dynamical mass becomes 0, at which point the joint initial value problem does not admit, it is not well posed once the dynamical mass becomes 0. Another reason to physically motivate this has to do with the n particle case, but we're going to leave that for a future talk. So at this point, I would like to address an elephant in the room, which is not particularly an elephant in this room, but it is an elephant in other rooms. Namely that physicists don't typically care about solving the joint evolution problem for a particle field system. Typically, at least the physicists that I talk to, are more interested in solving for the field given a charge current, or they are interested in solving for the motion of a test charge given an external field acting on it. So if we are given a field, then we can solve for the trajectory of a test charge via the force law, or given a charge, given a current in general, we can solve for the field that it generates via the field equation from earlier. And I would like to beg the following question, which is, what would happen if we were to create a sequence of these particle trajectories and fields recursively? I.e., if we essentially do this, I call it the physicist method, or the physics cycle, right, of field particle dynamics. If we do this recursively, we are given a field, and we use this to solve for the trajectory of a point charge, and then we use the trajectory of the point charge to solve for the next field that it generates, and then repeat this process over and over and over again. In the case of electromagnetism in 3+1 dimensions, this does not work, because if we were to do this, then we would find that the Lorentz force would be immediately undefined at the origin, at t is equal to 0. But in our case, where we have this well-defined force law, we find that we can create this recursively. And so, and in particular, we are interested in it with regards to the well-posedness of our solution, because if we can prove the convergence of the sequence to some unique trajectory / field solution, then we have proved global well-posedness. Because the whatever the unique trajectory / field solution is, if you were to take the field that you were given and plug it into the force law, the trajectory that pops out would be the same trajectory that gave rise to the field in the first place. And therefore, that would be a unique global and time solution to the joint initial value problem. And it is this is precisely the way that we are actually going to go about proving the existence of a unique global and time solution. So that is the intuition. The way that we are going to construct this sequence is actually by transforming our dynamical system into our dynamical equations into integral equations. So we recall that our scalar field, could be split up into two parts, one of which was already solved for, u free, because that was just the wave equation with some initial data that's given. It is u source that has not been solved for, because it depends on the trajectory of the particle. So this u source has this following integral equation. And we recall that the motion of our particle really only depended on u source evaluated along the trajectory of the particle. And so we don't really need to know u source everywhere in order to solve our joint IVP. The place that we only care about it is evaluate along the trajectory of our particle. And this has a much simpler form for our integral equation. And so in general, we are motivated to write down all of our joint initial value problem equations as a system of integral equations. The first integral equation is for the position. It's just given by integrating the velocity. The dynamical momentum is given by integrating the force law that we had from earlier. And W, which now represents the u source term that is evaluated along the trajectory of the particle, this is now just a function of time, is given by this integral. Notice now that this m star, our dynamical mass, is a function of the position of our particle, as well as this w term, because this w literally represents the u source term evaluated along q, along the trajectory of our particle. Okay, so ultimately, our goal is to prove the well-posedness of this integral equation. In other words, if you start off with a differential equation that is generally of the form of dq over dt equals f of q, then this is the same thing as searching for a unique solution to the problem of taking your trajectory, plugging it into your function f, integrating it, and the thing that you should get back was the original trajectory. So this is what we would like to find. We'd like to find a q, a p star, and a w, such that when I plug it into these functions and I integrate it, I get back the original.
Larry, I have a quick question.
Mm-hmm.
I mean, you might answer it in the proof of the theorem, but so this looks very similar to how one actually proves, existence and uniqueness of differential equations by turning it into an integral equation and then iterating. But in that case, you can only prove things local in time. But you've stated a theorem that proves something global in time. So I'm just curious as to how you get around that.
Yes. So I'm actually using Professor Kiessling's technique. I don't know if you remember, but he showed this to me in his class.
Yeah, I think I remember. I think that was my question, was if that was what's going to happen here. Okay.
Yes.
Okay.
I don't know if you remember. I was very excited that day when I saw
he did something like that in his classical mechanics class. right? Is this what you're talking about? Proving
This
like
is
Okay.
Yeah, this is
Perfect.
precisely it. So we have the following theorem, which I don't particularly want to attribute to directly Kiessling, because I'm not 100% sure if Kiessling is the one who came up with this specific proof. But Kiessling is the one who taught it to me in his class. If we have just an arbitrary integral equation of the form of 26, here I'm taking it to be on R3 cross time, r greater than or equal to 0, which is a function back into R3. If this is Lipschitz in space in R3 with a constant L for all time, and then we allow gamma to be some arbitrary number greater than L, and we allow y to be a complete set of trajectories in R3, our continuous maps from time into R3, with this following weighted norm. And if we can define f star, which takes a trajectory in y, plugs it into f and it integrates it. If that spits out another trajectory which is also inside of y, then we find that this f star is a contraction mapping on y. And this necessarily implies, by the Banach fixed point theorem, that y contains a unique fixed point which satisfies the integral equation. And this is the main theorem which was used in our paper in order to prove the well-posedness of our system. Essentially, we just looked at these equations, which look very messy. We proved that they are all Lipschitz with respect to our variables. And we also proved that we constructed a capital Y such that it mapped Y into itself. And we were done. We had global well-posedness. So I don't want to get into the details, because proving that this F is Lipschitz in this case is quite messy. But it's also not particularly difficult. It's just computational heavy. So this was the way that we proved global well-posedness. So now that we have well-posedness, we want to ask ourselves the most interesting question, which is, what is the effect of the self-force on our trajectories? So recall that we have our force law, which I've now written in terms of the rate of change of the proper velocity. And it is given by a self-force term, which is given by this, and then the external force terms. If our external radiation was initially compactly supported, then after some finite time, we can show that these external radiation force terms vanish. And that is essentially because the radiation comes through, it propagates, it hits the particle, but since it's moving at the speed of light, it very much leaves after some finite time. And after this point, the only thing that we have left is the self-force term, which should be causing the particle's velocity to decay. And that is precisely what we prove, namely that for the particle's velocity becomes arbitrarily small for arbitrarily large times. And we will also prove a growth rate in the worst case scenario, a decay rate in the worst case scenario. So in this proof of this theorem, we're just going to assume that this theorem is true because of the heuristical argument that I gave before. There's a more rigorous proof that one can give. But assuming that the external force vanishes in finite time, all we have to do at this point is prove that this self-force term causes the velocity to decay. However, one should be afraid that if the dynamical mass grows too large too quickly, then it may not fully decelerate to rest. For instance, if this m star grows exponentially, then you very much will not go towards rest. However, another theorem that we prove in our paper is that the dynamical mass only grows at most linearly. So we have this bound that m star is, for large time, less than or equal to a times x0. And once we have this, all we need to do is integrate the force law in the case that you only have the self-force term. You divide both sides by the proper velocity, you integrate both sides, you find that the natural log of the proper velocity is equal to negative a squared over 2 times the integral from t to x0 of 1 divided by the dynamical mass. But since 1 divided by since this quantity is less than or equal to the same, but with the integral being replaced by 1 over a times x0, we ultimately find this inequality. If we exponentiate both sides, then we find that the proper velocity is going to be decaying. In the absolute worst case, in the case that it is this linear growth, then we have that it is decaying at most polynomially in time, is what I'll say, with the power being given by this negative a squared over 2. Which is intuitive, because if you take the charge to be very, very small, then you would expect the self-interaction to be very, very small, and so it would take much longer in order for the particle to, for the self-force to cause it to decay. Does anyone have any questions about this? Okay, so I have some simulations. So these are more simulations. These look a little bit less cool than the other, but they're prettier. This represents a particle originally at 0, whose motion is being perturbed by some external radiation. We see that it accelerates to the right, and then you can see it starts to, sorry, time is the vertical axis, space is the horizontal. The particle, after the external radiation leaves, which is quite quickly, the particle starts to have its self-force, starts to feel its self-force, and the velocity decays. If you do the simulation, but for a longer time, you'll see that it very much reaches rest quite quickly, or reaches approximately rest very quickly. So
what do the colors mean?
this color means the this color is the field that is sourced by the particle. So this is the freely evolving stationary state solution plus the U source. And you can see here that the particle's world line directly follows where the derivative of our field is singular. That's why I included the force. So right here is where it, I suppose it's bright colors, so you can't really see that there is a singularity. It's a singularity in the derivative. But along the particle's world line is where this derivative jumps.
So the color looks continuous. So but this is the field, not the derivative of the field.
Yes, yes. I suppose I could have had the derivative of the field instead. That maybe would have been cleaner. Or yeah.
No, but that's okay. It's you have to, when you think of horizontal slices, yeah, that is pretty much like a little bit deformed tent, which you showed earlier.
Right, but I mean, we don't know that it is a tent rather than a parabola or something.
Yeah, it is.
When you get further away from the line, no, from that black line, go to the left when you are high up there in the graph at late times. No? If you go to the left, you see you come from the yellow over to the green, and then gets darker blue, and at the right, the color code shows that it is more and more negative values. No? So it is really dropping off. No? So it's not a parabola really, but
no, I mean, it is dropping off. Yeah, it doesn't show that there is a kink there.
Yeah,
I guess that's what you wanted to
you
show.
mean at the singularity?
At the singularity,
yeah.
right?
Yeah, okay.
This is much better.
This shows it.
Right. Right. This shows the kink. That it is in fact a kink, and the kink is always there.
Okay.
And this is a different simulation than this one. This one was just a single bump of radiation, as opposed to the other one, which was oscillatory. All right. So yeah, that is the end of our talk in review. In this talk, ultimately, we study the dynamics of a particle coupled to a scalar field in one space dimension. We use local conservation of energy to the assumption of local conservation of energy to derive a unique force law, which describes the motion of our particle. We show that this force law is in fact admissible, and it gives rise to a well-posed joint initial value problem for our field particle evolution. And lastly, we study the asymptotic behavior of this stationary particle perturbed by radiation, and found that it asymptotically returns towards rest. We would very much like to thank Vu and Maria for pointing out this error. And yeah, in regarding future work, we have a lot of future work, because you'll notice that this presentation is the same as last time. We've actually done a lot since then, and we have a lot of ideas. We're very excited. So potential things that we are interested in is extending the well-posedness result to the case of n scalar particles. And we have, in fact, already done this, and we plan to present this soon. Another case that we're interested in studying, that I'm currently studying with the help of 2 undergrads, Aditya and Ethan, is the massive scalar field case. You have alpha greater than 0. We're interested in seeing if this gives rise to a different self-force or a similar one. We are also interested in studying a quantum version of this joint initial value problem. So namely, we replace the force law that's given by that, we replace our force law with a velocity law, a quantum Bohmian law of motion. And the idea is that the scalar field which appears in the equation for the wave function is actually sourced by the particle, which is guided by that same wave function. So that is an initial value, a joint initial value problem that we're very interested in studying. And in terms of general relativity, we're also interested in trying to study the joint evolution problem of a point particle, where it is now acting as a singularity in the curvature of space-time. So that is the end of our talk. We have our references. This is Kiessling's paper on his K-force, his Kiessling force. This is Vu's paper, where they prove the well-posedness of the BLTP in 3+1 dimensions. And then this is a textbook. So I hope that you all enjoyed, and feel free to ask questions.
Thanks a lot.
Let's thank the speaker.